You walk into a dark room. Your hand finds the switch on the wall. You flip it up. The light turns on instantly. That's normal. That's what lights do. You've done this 10,000 times in your life and never questioned it. But here's what you probably believe is happening in that moment. Electrons are racing through the wire from the switch to the bulb, racing fast, maybe at the speed of light, carrying energy like tiny trucks on a highway, delivering power from the wall to the filament. That picture lives in your head because someone put it there. A teacher, a textbook, a diagram with arrows showing current flowing through a circuit. The arrows move, the electrons move, everything makes sense. But that picture is wrong, not slightly wrong. Not wrong in some technical way that doesn't matter, fundamentally wrong. Wrong in a way that changes what electricity actually is, and the truth is stranger. The truth is that when you flip that switch, the electrons in the wire barely move at all. They drift slowly, painfully slowly. So slowly that if you could watch a single electron, you'd lose your mind with boredom. We're talking millimeters per second, sometimes slower. A snail moves faster than the electrons in your wire. So how does the light turn on instantly? That's not a rhetorical question, that's the question. The question that breaks the simple story you were told. Because if electrons move slowly and the light turns on fast, then something else is happening. Something else is carrying the energy, something else is moving through that wire at nearly the speed of light. But it's not the electrons. What is it? Let's go back to school. You're sitting in a classroom. The teacher draws a wire on the board. Inside the wire, little circles, those are electrons. The teacher draws arrows on the circles. The arrows all point the same direction. Current, the teacher says, current is the flow of electrons. When you close the circuit, electrons flow. They carry energy from the battery to the light bulb. The more electrons flow, the brighter the light. Simple, clean, wrong. Here's what they didn't tell you. That picture works mathematically, but it's not what's actually happening. It's a useful fiction. A model, and models are tools, they're not reality. But somewhere along the way, the model became the explanation. The map became the territory, and now you believe electrons race through wires. Let's test that belief. Take a copper wire, 1 meter long. Connect it to a battery, a typical household current. Now ask yourself, how fast do the electrons move through that wire? You might guess fast, very fast, maybe thousands of meters per second. After all, electricity seems instant. The actual answer is about 1 millimeter per second. 1 millimeter per second. That's not a typo. That's not an approximation. That's the drift velocity of electrons in a typical copper wire carrying typical household current. If you marked an electron at one end of a meter-long wire, it would take about 16 minutes to reach the other end. 16 minutes, but when you flip a switch, the light turns on in less than a nanosecond. So the light is not waiting for electrons to arrive. The energy is not being carried by the motion of electrons. Something else is happening. Let's slow down. Let's think about what a wire actually is. A copper wire is a lattice of copper atoms, billions upon billions of them locked in a crystalline structure. Each copper atom has electrons. Most of those electrons are bound tightly to their atoms. They don't go anywhere, but copper has what we call free electrons. Loosely bound, 1 per atom, roughly, and these free electrons can move. But here's the thing, they're already moving. Even before you connect the battery, even before you flip the switch. These electrons are moving randomly, bouncing around, colliding with atoms, changing direction thousands of billions of times per second. The motion is chaotic, thermal. The electrons are vibrating at hundreds of kilometers per second in random directions. Now you connect a battery. What happens? The battery creates an electric field in the wire. That field pushes on the electrons, all of them at the same time, and the electrons start to drift very slightly, in one direction, but they're still bouncing around randomly. The drift is just a tiny bias added on top of the chaos. Imagine a crowded room full of people walking randomly, but there's a gentle breeze pushing everyone slightly toward one door. That's drift. The drift is slow because the electrons keep colliding with atoms. Every collision resets their direction. They accelerate for a fraction of a nanosecond, then bang into an atom, then accelerate again. On average, they make almost no progress. The drift velocity is this tiny, tiny average motion in one direction, so the electrons are not racing. They're stumbling, drunkenly, in the general direction of the positive terminal. But here's what matters. Every time an electron collides with an atom, it transfers energy, kinetic energy. The atom vibrates more. That vibration is heat. That's why wires get warm. That's where the energy goes. Not into the motion of electrons, into heat. Electrons are not energy carriers, they're energy losers. So, if electrons don't carry the energy, what does? The electric field. Stay with me. An electric field is not a metaphor. It's not a mathematical convenience. It's a real physical thing that exists in space. When you connect a battery to a wire, the battery creates a difference in electric potential between its terminals. Positive on one end, negative on the other. That potential difference creates an electric field along the wire. The field appears almost instantly. Not quite instantly. Nothing travels faster than light. But the field propagates through the wire at a significant fraction of the speed of light. Somewhere between 30% and 90% depending on the wire and the insulation. Fast enough that for most practical purposes it seems instant. The field fills the space around and inside the wire. And here's the critical point. The field carries the energy, not the electrons. When you flip the switch, you're not sending electrons on a journey. You're closing a circuit. You're creating a continuous path for the electric field. The field was already there, waiting. The moment the circuit closes, the field configuration adjusts. Almost instantly, and energy begins to flow. But not through the wire. Around it. This is where it gets strange. The energy in an electrical circuit flows through the electromagnetic field in the space surrounding the wire. Not inside the copper, outside, in the insulating material, in the air, in the space between the wires. The electrons inside the wire are just jiggling in place, colliding with atoms, creating the conditions for the field to exist, but they're not the energy. They're the medium. The field is the message. Let's go back to the light switch. You flip it, the light turns on. What actually happened? When you closed the switch, you completed the circuit. In that instant, the electric field configuration throughout the entire circuit adjusted. Not because the electrons raced from the switch to the bulb, but because the field is a continuous entity. Changing the field in one place affects the field everywhere else. Almost instantly, think of it like a long tube filled with water. The tube is 10 meters long. You push on the water at one end. Does the water at the far end move instantly? No. The water molecules at your end push the molecules next to them, which push the molecules next to them, and so on. That's a compression wave. It travels at the speed of sound in water. Fast, but not instant. But now imagine something different. Imagine the tube is completely rigid and completely full with no compression possible. If you push on the water at one end, the water at the far end has to move at the same instant. Because water is incompressible and the tube is rigid, the motion is transmitted instantly. That's closer to what's happening with the electric field. Not perfectly accurate, the field doesn't propagate instantly. It propagates at the speed of light in the medium. But that's fast enough that for a wire in your house, the delay is unmeasurable. A wire 10 meters long. The field propagates across it in about 30 nanoseconds. You cannot perceive 30 nanoseconds to you. It's instant. So the light turns on instantly not because electrons arrived instantly, but because the field configuration changed instantly. The field was already everywhere in the circuit. It was just waiting for the switch to close. When the switch closed, the field knew, everywhere, immediately, and energy began to flow. We need to talk about current, because current is real. Current is measurable. You can stick an ammeter in a circuit and measure current, and the ammeter will tell you how many amperes are flowing through the wire. And an ampere is defined as a certain number of electrons passing through a cross-section of wire per second, so electrons are moving, right? Yes, but here's what current actually measures. It measures the collective drift of an enormous number of electrons. Not the motion of individual electrons, the drift. Imagine a pipe full of water. The water molecules are vibrating randomly, bouncing off each other. But on average, there's a net flow in one direction. That net flow is what you measure when you measure current. You don't care about the random vibrations. You care about the average motion, same with the electrons. Current tells you the net drift, the average, and that drift is slow. But the number of electrons is so large, so incomprehensibly large, that even a slow drift corresponds to a lot of charge moving past a point per second. A lot of amperes, 1 ampere means about 6 billion electrons passing through a cross-section of wire every second. 6 billion, that's a lot of electrons. But each one is moving at millimeters per second. They're not racing. There are just a lot of them, so current is real. But it's not what you think it is. It's not fast electrons, it's slow electrons in enormous numbers, drifting collectively. And still, they're not carrying the energy. There's a piece of mathematics that describes where energy flows in an electromagnetic field. It's called the Poynting vector. You don't need to understand the math. But you need to understand what it tells us. The Poynting vector points in the direction of energy flow. And it's calculated from the electric field and the magnetic field at each point in space. And here's what it shows. In a circuit, the energy flows through this space around the wires, not through the wires themselves. The Poynting vector points radially inward toward the wire and also along the direction of the circuit. Energy is flowing from the source through space toward the load. The wire is just a guide, a boundary condition. The electrons in the wire create a current, and that current creates a magnetic field, and the interaction between the electric field and the magnetic field determines where the energy goes, but the energy is in the fields, not in the electrons. This is not controversial. This is mainstream physics. This is what every electrical engineer knows, even if they don't think about it every day. The energy in a transmission line flows through the space between the conductors, not through the conductors, through space. In a coaxial cable, the energy flows through the dielectric insulator between the inner and outer conductors, not through the metal, through the insulator. The part that doesn't conduct, that's where the energy is. That's where it's always been. People love analogies. Electricity is like water in a pipe. Voltage is like pressure. Current is like flow. Resistance is like a narrow section of pipe. It's a useful analogy. It helps people get started. It gives them intuition. But it's wrong in the most important way. In a pipe, the water carries the energy. When water flows from a high place to a low place, the water itself has potential energy. When it flows fast, it has kinetic energy. The water is the thing, the substance. The medium and the message. Electricity is not like that. The electrons are not the thing. They're barely moving. They're not carrying energy. They're facilitating a field. The field is the thing. The field is what moves. The field is what carries energy. There is no substance flowing through the wire in the way water flows through a pipe. There's a field surrounding the wire, and that field is real, and that field is where the energy is. This is hard to accept because fields are invisible. Water you can see. water makes sense. You can put your hand under a faucet and feel the water hit your hand. You can catch it in a bucket. It's tangible. Fields are not tangible, but they're real. More real, in some sense, than the electrons. You might be thinking, so what? The light still turns on, the phone still charges, the toaster still toasts. Who cares whether it's electrons or fields or magic fairy dust? Here's why it matters. Because the model you have in your head determines what questions you can ask. And the wrong model makes you blind to certain questions. If you think electricity is electrons racing through wires, you'll never wonder why the energy can flow through a vacuum. You'll never wonder how radio waves work. You'll never understand why a transformer works, why there's no physical connection between primary and secondary coils, yet energy flows from one to the other. The wrong model makes those things seem like magic. The right model makes them inevitable. A radio wave is an electromagnetic field propagating through space. No wires, no electrons, just fields, electric field and magnetic field oscillating together, carrying energy through empty space at the speed of light. That energy can travel across the universe. It can travel for billions of years. And when it reaches your antenna, the field induces a current in the metal. Not because the electrons traveled from the star, but because the field arrived and the field pushed on the electrons that were already there. The electrons in your antenna never left your antenna. They just responded to a field that came from light years away. That's what's really happening. And once you see it, you can't unsee it. Let's talk about resistance. In the simple model, resistance is just friction. The electrons are trying to flow and the atoms get in the way. More resistance means more friction means more heat. That's not entirely wrong, but it's incomplete. Resistance is really about how the electrons interact with the lattice of atoms. Every collision between an electron and an atom transfers momentum and energy. The electron loses kinetic energy. The atom gains vibrational energy. That vibration is heat. But here's the key insight. Resistance is what allows the electric field to do work. Without resistance, there's no energy transfer. In a superconductor where resistance is zero, electrons can drift without colliding. They move freely, and because they're not colliding, they're not transferring energy to the lattice. No heat. The field exists, the current flows, but no energy is dissipated in the wire. That's why superconductors are so useful and so weird. In a normal wire, resistance is the mechanism that converts field energy into heat. The field pushes the electrons collide with atoms. The atoms vibrate. That vibration is thermal energy. That's where the energy from the field goes. So resistance isn't a bug, it's a feature. It's how the field gives up its energy. Think about a battery, a chemical battery. The kind you put in a flashlight. Inside the battery, there's a chemical reaction happening. That reaction creates a separation of charge. Positive charge accumulates on one terminal, negative charge on the other. This separation creates a potential difference, voltage. Now connect the battery to a wire. The voltage creates an electric field in the wire. The field pushes electrons. The electrons drift slowly. They collide with atoms. Energy is dissipated as heat, but where did the energy come from? Not from the motion of the electrons, they're barely moving. The energy came from the chemical reaction in the battery. The reaction converts chemical potential energy into electrical potential energy. That potential energy exists in the electric field. And the field delivers that energy through space to the resistor where it's converted into heat. The electrons are just the middlemen. The battery doesn't send electrons on a journey, it creates a field. The field exists in the space around and between the battery terminals and the load. And the field is where the energy is. When the battery dies, it's not because it ran out of electrons. Electrons don't get used up. The battery dies because the chemical reaction stops. No more reaction means no more potential difference means no more field means no more energy. The electrons are still there. They were never the point. Let's scale up. Forget about the wires in your house. Think about a power transmission line. The big ones, high voltage, hundreds of miles long, carrying power from a generating station to a city. Those lines carry enormous amounts of energy, gigawatts, enough to power millions of homes. Where is that energy? It's not in the metal. The wires themselves don't store significant energy. The energy is in the electromagnetic field surrounding the wires. The space between the wires, the air, that's where gigawatts of power are flowing. Through the air. The wires are just guides. If you could see the pointing vector, you'd see energy streaming through space, parallel to the wires, in the region between them. The wires define the boundary conditions for the field. They create the geometry. But the energy is in the space, and this is why high voltage transmission is more efficient. Higher voltage means stronger electric field. Stronger field means more energy can flow through a given space. You can transmit more power with less current. Less current means less resistive heating in the wires. Less loss. The energy was always in the space. We just had to learn how to use that space efficiently. Let's go back to the speed question. People ask, if electrons move slowly, why does the electricity seem so fast? The answer is now clear, because the electrons don't need to move fast. The field propagates fast. The field is what matters. But there's another misconception here. People think of electricity as something traveling from point A to point B, like a package being delivered. The package starts at the power plant, travels through the wires, and arrives at your house. That's the mental model. But that's not how it works. The field is everywhere in the circuit, all at once. When you close the switch, you're not sending a signal that travels to the power plant. You're changing the boundary conditions of the field. The field responds everywhere simultaneously at the speed of light in the medium. It's more like pressing on a balloon. Press one side and the other side bulges out instantly. Not because air molecules raced from one side to the other, but because pressure is a field. Change the field in one place and the whole field adjusts. Electricity is like that. Change the circuit and the field adjusts everywhere, almost instantly. So, what is electricity? It's not a substance. It's not a fluid flowing through wires. It's not electrons racing from source to load. It's a configuration of fields in space. The electrons are there, they're real, they're moving. But they're not the essence of the thing. They're a side effect, a necessary condition, but not the phenomenon itself. This is deeply counterintuitive because we like substances. We like things we can point to and say, that's what's moving. Water flows, air flows, traffic flows. We extend that intuition to electricity. Current flows. But current isn't a thing that flows. Current is a measure of a collective behavior, a statistical average. It's a number that describes how many electrons are drifting past a point per second. It's useful, it's measurable, but it's not what's actually happening. What's actually happening is that a field exists in space, and that field has energy, and that energy propagates through space, guided by conductors. And when the field encounters resistance, the field gives up its energy to the material, and that energy becomes heat or light or motion. The electrons are just there to make it possible. They're the stage, not the actors. So, why do textbooks teach the simple model? Why do teachers draw arrows on electrons and say, this is current? Because it works for most purposes. The simple model is good enough. If you're designing a circuit, calculating voltage drops, sizing wires, you can treat current as a flow of electrons and get the right answer. The math works out, the predictions are accurate, and the simple model is teachable. You can explain it to a 12-year-old. You can draw pictures. You can use analogies, water and pipes. Marbles rolling down a ramp, it's intuitive. The field model is not intuitive. Fields are abstract, you can't see them. You can't touch them, you need vector calculus to describe them properly. You need Maxwell's equations. That's a high barrier, so we teach the lie first. And for most people, the lie is enough, but it's still a lie. And if you want to really understand what electricity is, you have to unlearn it. You have to accept that your intuition is wrong. You have to embrace the field. Let's go back to where we started. You're standing in a dark room. Your hand finds the switch. You flip it up. The light turns on. Now you know what happened. You closed a circuit. In that instant, the electric field configuration throughout the circuit adjusted. The field had been present all along, waiting. The source was creating a potential difference. The wire was filled with free electrons, vibrating randomly. But the circuit was open. The field had nowhere to go. When you closed the switch, the field completed its path. Energy began to flow from the source to the load. Not through the wire, around it, through the space surrounding the wire. The energy propagated at nearly the speed of light, arriving at the bulb in nanoseconds. At the bulb, the field encountered resistance, the tungsten filament. The electrons in the tungsten were pushed by the field. They collided with tungsten atoms. Those collisions transferred energy. The atoms vibrated faster, hotter, hot enough to glow, hot enough to emit visible light. The light turned on. Not because the electrons raced from the switch to the bulb, but because the field was already there and the field carried the energy, and the energy became light. We live in a world of fields. Electromagnetic fields surround you constantly. Radio waves, cell phone signals, the light from the sun. The glow of your screen, all of it is electromagnetic fields carrying energy through space. And electricity in wires is just one manifestation of that. The field in a wire is the same kind of field that propagates through empty space as a radio wave. Same physics, same equations, the only difference is the boundary conditions. The wire constrains the field, guides it, shapes it, but the field is the fundamental thing. Once you see this, everything changes. A radio tower doesn't send electrons into the air. It creates an oscillating electromagnetic field. That field propagates outward at the speed of light. When the field reaches your antenna, it induces a current. The electrons in your antenna respond to the field. They oscillate. That oscillation can be detected and decoded. But nothing traveled from the tower to your antenna except the field. No particles, no substance. Just the field, and the field carried the information. The field carried the energy. The field is the medium and the message. We started this by talking about how the water analogy fails, but all analogies fail eventually. Because electricity is not like anything else, it's its own thing. You can compare it to water, or traffic, or crowds of people, and those comparisons help you build intuition. But at some point, you have to let go of the analogy and deal with the thing itself. And the thing itself is strange. It's a field. An invisible, intangible configuration of space. But it's real. It carries energy. It exerts forces. It propagates at the speed of light. It can be measured, it can be calculated, it obeys precise mathematical laws. And it's not like water. Water is made of molecules. Molecules are made of atoms, atoms are made of particles. It's turtles all the way down, but at least there are turtles. The electromagnetic field is not made of anything. It's fundamental, it's one of the basic constituents of reality. As far as we know, the field is not made of smaller parts. It's not an emergent property of something deeper. It's just there. Space has the capacity to support electromagnetic fields. That's a fact about space, a fact about the universe. And electricity is what we call it when we manipulate those fields for practical purposes. Now that you know this, you can't go back. You'll flip a light switch and think about fields. You'll charge your phone and think about energy flowing through space. You'll see power lines and know that gigawatts are streaming through the air between the wires, not through the wires themselves. The simple model is broken for you now, and that's good. Because the simple model was always inadequate. It was a stepping stone, a scaffold, useful for a time, but not the final answer. The final answer is stranger and more beautiful. Because once you see that electricity is really about fields, you start to see fields everywhere. Gravity is a field. The strong nuclear force is a field. The weak nuclear force is a field. Quantum mechanics is built on fields. The Higgs field gives particles mass. The universe is made of fields. Particles are just localized excitations of fields. Everything is fields. And electricity was your first introduction to that truth. You just didn't know it yet, so we've answered the question. Electricity doesn't flow the way you thought. Electrons drift slowly. The field carries the energy. The energy flows through space, not through the wire. But there's a deeper question. What is the field? We can describe it mathematically. We can measure its effects. We can predict its behavior with extraordinary precision. But what is it? What's actually there in the space around the wire? We don't know. Not really. The field is a solution to an equation. It's a pattern of numbers assigned to every point in space. It has magnitude, it has direction, it changes over time. And when we do experiments, the universe behaves as if those numbers are real. But are they? Or is the field just a calculational tool? A way of organizing our predictions? Physics doesn't answer that question. Physics tells you what will happen. It doesn't tell you what things are. And maybe that's the right place to end. You flip the switch, the light turns on. You know more than you did before about what happened in that moment. You know it's not the electrons racing through wires. You know it's a field, adjusting, carrying energy through space at the speed of light. But you don't know what the field is. No one does, and maybe no one ever will. The universe is under no obligation to make sense to you. It just has to be consistent. And it is. The light turns on every time.